We're going to work through a statics problem that involves a ladder. So here we have a uniform ladder of 10 meters long, and it weighs 50 newtons, and it's resting against a smooth vertical wall. So this wall here is frictionless, but the ground down here does have friction. So if the ladder is just on the verge of slipping when it makes an angle of 50 degrees with the ground, we're going to find the coefficient of static friction between the ladder and the ground. So this was a problem. If you've been watching the crash course physics videos, which I hope you do, this was a problem that they went through in one of the crash course astronomy or crash course physics videos about statics. So this is what we call a statics problem, where everything is stationary and we have to take into account our two conditions for equilibrium: that the sum of our forces has to equal 0 in our problem, and the sum of the torques has to equal 0 in order for everything to be stationary. Okay, so we got to find the coefficient of static friction. We only know these two pieces of information and the angle. Okay, so where shall we start? Well, we said we have to use both of our conditions for equilibrium. So let's just start. Well, before we start with, I'm going to start with the sum of our torques in our problem. Let's draw the free body diagram of this. Okay, so we've got our ladder. Okay, so the ladder we're going to assume is uniform. So its center of gravity, where we can draw the free body diagram where all of its weight can be centered, is at half its length. So if this whole thing is 10 meters, then our weight of the ladder is going to be centered at 5 meters, halfway along its length. So I'm going to draw in the weight of my ladder right here. I'm going to call it W sub L for the weight of the ladder. And so the distance from here, where it's touching the ground, to where that weight is centered is at half its length, 5 meters. Okay. And then we have the force up here that the wall is exerting on the ladder. And that force goes in this direction. So this is the force that the wall is exerting on the ladder, and I'm going to call that F sub W for the force of the wall on the ladder. And then we have the friction force down here, which is going to oppose the direction that the ladder will want to slide. So the ladder is going to want to slide this direction, so our friction force is going to oppose that. So let me draw in that arrow a little bit thicker. Okay, and then we've got the normal force from the end of this ladder resting on the ground, and that normal force is going to be pointing upward here. Okay, so that's the free body diagram for my ladder. Okay, now we've got to think about the sum of our torques. Okay, so that's our first condition. The sum of torques has to equal 0. Now if I come over here and I look at all those 4 forces in my problem, those are each going to have a torque associated with them. And we're going to assume, well, we can pick wherever we want to be the pivot point around which we calculate our torques, but I'm going to put it right here at the ground. You can pick it wherever you want. You might as well place it strategically to help you a little bit in the problem. So I'm going to put it right here where the ladder touches the ground, the pivot point. Pivot. Okay, so we've got the torque coming from the normal force. We've got the torque coming from the friction force. And we've got the torque coming from the weight of the ladder, and then the torque coming from the wall on the ladder up here. And the sum of all those torques has to equal 0. Now, here, the force, the normal force on the ladder and the friction force on the ladder are right at the pivot point. So then those torques are 0, and they're not going to contribute here to our problem if I choose that point strategically as my pivot point. Okay. Now let's think about the torques on the ladder and the torque from the center of mass of the ladder and the torque from the wall. I wasn't careful to take care of the positive or negative signs on these torques. So let's think about that. Okay. So if I come over here, let's look at the torque coming from the center of mass, the center of gravity of my ladder. Okay, the place where we can assume where all the weight is essentially centered for this ladder for this problem. So if everything revolves or rotates around this pivot point, okay, if I remove the wall, in which direction is my ladder going to fall? It's going to fall this way. just due to the weight of the ladder. Okay, that is in the direction of the clock. That's the direction that our hands move on the clock. That's clockwise. Clockwise torques are negative. So this is actually a negative torque here. Okay, so I need to put a minus sign right here on the torque from the weight of my ladder. Okay, and then when I think about the torque that's coming from the force pushing on the ladder at the top here. Okay, so if all I have is the pivot point right here, don't think about the weight of the ladder, and I try to tug on this ladder up here along this direction of this force, that's going to cause the ladder to rotate this direction. It's going to cause the ladder to go in that direction. Imagine pulling it. We're going to move our ladder this way, okay? And so that motion, that rotation, is a counterclockwise torque. That's opposite the direction that the hands move on our clock. So this is going to be a positive torque, okay? So this positive sign here is good. And so then I've got minus the torque from the ladder, center of gravity, plus the torque from the wall on my ladder equals 0. So then if I'm going to move my negative term to the other side. So I've got the torque from the wall has to equal the torque from the center of gravity of the ladder. So the torque from the wall, remember torque is equal to RF sine theta. Okay, so this distance r for the force on the wall, from the wall on the ladder, this distance r is the entire length of my ladder. So I'm just going to call that L, okay? The entire length of the ladder is R here, times the force that the wall is exerting on the ladder, so I'm going to call it F sub W. This angle theta, the angle between our force and this, distance between the pivot and where that force is being applied. So if this angle down here is 50 degrees, okay, this force is parallel to the ground. And so we've got this ladder here, we've got an angle here, and then we've got this angle here. These are alternating interior angles. Alternating interior angles are congruent from geometry. So this angle up here is also 50 degrees. So this is going to be the torque from the force of the wall on the ladder is going to be the length of my ladder times this force that the wall is exerting on the ladder times sine of this angle, which was 50 degrees. Okay? And that equals the torque from the center of mass of my ladder, which is going to be centered at half the length of my ladder. So R for this torque is going to be L over 2 times the weight of the ladder times sine of the angle. And that angle is going to be the angle between our applied force and this radial distance here that I can draw from the pivot to where that weight, center of gravity of the ladder is applied. Okay, so what is that angle? If I come over here, I've got a little right angle triangle here. If I draw my weight straight down, we've got a perpendicular 90 degrees here. We've got our angle 50, and then we have this angle up here, which I'm going to call angle alpha. Okay, so the total sum of all the angles in a triangle is 180 degrees. So we have 180 degrees is equal to our 90 degree right angle here, plus our 50 degree angle here, plus this angle up here that I'm going to call alpha. Okay, so if I solve this equation for alpha, I have to take 180 minus 90 minus 50, then alpha is going to equal 40 degrees. So this is going to be L over 2 times the weight of my ladder times sine of this angle alpha here. So we can solve this equation for the force that our wall exerts on the ladder. So let's do that. Oh, and even before I do that, I see that there's an L on this side, there's an L on that side. Actually, the length of my ladder cancels out on both sides. So the force that the wall exerts on my ladder is 1/2 times the weight of my ladder times sine of my angle alpha divided by sine of my angle theta. Okay, so if I go ahead and plug this in, I've got 1/2 times the weight of my ladder, which was 50 newtons, times sine of my angle alpha, which was 40 degrees, divided by sine of my angle theta, which was 50 degrees. And that gives us 21 newtons. That's the force that our wall is exerting on the ladder in this direction. Okay, but that hasn't helped us yet get our coefficient of static friction. So what we're going to do now is apply our second condition for static equilibrium. We did our sum of torques equals 0. Now we've got to do our sum of forces equals 0. And guess what? We've got forces in the x and the y direction. So we have to apply Newton's second law for statics in both directions as well, x and y. So we've got the sum of all the forces in the x direction has to equal 0. Okay, that's our second condition. 1, 2. Okay. For our forces in the x, we've got the friction force pointing in the positive x direction. We've got friction force, and then we've got the force that the wall exerts on the ladder pointing in the negative x direction. So we've got friction force minus the force from the wall equals 0. So our friction force equals the force from the wall. Friction force, remember, you guys, you got to use the equation sheet. Have the equation sheet with you when you're doing any of your homework problems, any of your quizam stuff, even when you're doing lab stuff. Okay, so the force of friction is equal to our coefficient of static friction in this case, because we're not moving, times the normal force. And that equals the force that the wall exerts on the ladder. So our coefficient of static friction is going to be the force that our wall exerts on the ladder divided by the normal force that the ground is exerting on the ladder. Okay, so we already found what this force that the wall exerts on the ladder is. To get the normal force, we've got to do Newton's second law in the vertical direction, and we'll find that. So we do Newton's second law in the vertical direction has to equal 0. 0 equals, okay, forces in the vertical direction. We've got the normal force up, and we've got the weight down. So we've got Fn minus weight of the ladder equals 0. So our normal force is just equal to the weight of our ladder. Okay, so we can come over here to our coefficient of static friction. We can plug in the force that the wall exerts on the ladder, 21 newtons. Divide that by the normal force, which was equal to the weight of our ladder, which was 50 newtons, divided by 50 newtons. So then our coefficient of static friction is equal to 0.42. So that's the coefficient of static friction we need to have between the ladder and the floor and the ground so that our ladder doesn't slip.